Hi, welcome to another do-it-yourself video. I'm Flavio Cavalieri, Papa Yankee 2 Foxtrot Golf Charlie. We're gonna present you now an upgrade version to our GAMBIARRA 1 project. If you remember this project, it's a transceiver for CW mode. We're gonna add now some features. We're gonna add phone mode to this project, and in a few minutes you're gonna see this project running and how it works inside the modifications we did to have this possibility now. So stay on few more minutes. Okay, for the simulation we're gonna present you the primary version of our QRP, the CW mode, which will be manipulated by our homemade manipulator as well. And next we're gonna present you the phone mode. So you're gonna use a standard CB radio microphone, PTT, in order to switch and in order to modulate the audio in our QRP newer project. And a few minutes later I'm gonna explain you a little bit the concepts behind the modifications we did in this guy to be possible to transmit our voice as well. So you're gonna set up here our antenna, a altimeter, the QRP, the transceiver, and we're going to start with CW mode. And if you see here interface, we are connected through the receiver to the internet HF receiver, the SDR, software defined radio, from the city of Pardinho, São Paulo. I'm in the 7050 megahertz. Okay, I'm in the 7.05 megahertz frequency in the 40 meters band. And if you see in the map here, the distance is about 150 kilometers from our city, Paulínia, to the Pardinho receiver. So I'm gonna use about 4 to 5 watts CW, and we wanna reach the receiver here in Pardinho. So I'm gonna present you now this application. So just to give you an overview here, I'm gonna put more on the right side here. You can see the city of Pardinho. It's located in the countryside of the São Paulo state, and we are here. I'm here in Paulínia, so it's about 150 kilometers. And so let's try to do now the transmission and see what's happening. So I'm gonna basically send here a CQ, a calling. Okay, I'm gonna enable the audio, so you're gonna listen directly the receiver from Pardinho. I'm gonna zoom it just to show you here the spectrometer. So let's transmit now our calling in CW. So this is the transmission. We call the CQ, test QRP, QRP test, and my call sign Papa Yankee 2 Foxtrot Golf Charlie. So this is the first test. Now we're gonna show you the audio, the phone mode we just implemented. Okay, and for the phone mode, the only thing I have to change here is my bandwidth. Okay, in this receiver interface. So I'm working here now with a 500 Hertz BW bandwidth. This is good for CW, fits for CW. I'm gonna now up my bandwidth to 1.2 kilohertz or even more. So it automatically changes a relay here and move to phone mode. So I'm gonna just put here for a good reception 2.2 kilohertz, and I'm gonna explain later on the circuits behind that. I'm in the 7.05 kilohertz, okay, megahertz, sorry. This is the 40 meter bands, 7050 kilohertz. So I'm gonna now try to transmit as you at the same time are listening the receiver in Pardinho. So I'm gonna call a CQ test here in the microphone. CQDX, CQDX. This is Papa Yankee 2 Foxtrot Golf Charlie. As you can see here in the spectrometer, my audio was transmitted, but I'm still here in CW mode in the receiver side. So I'm gonna just skip that. I'm gonna change to the LSB. You see the difference now in the audio. I'm in lower sideband right now. The mode I'm operating now, lower sideband, and I'm gonna transmit. And you're gonna see here in the spectrometer my modulation just working. So just change here to 70, okay, 7050 kilohertz, and let's play. CQDX, CQDX. This is Papa Yankee 2 Foxtrot Golf Charlie. Testing QRP. CQDX, CQDX. Papa Yankee 2 Foxtrot Golf Charlie. Testing QRP. And as you can see by my microphone recording my audio here in my check, you see a delay, a difference between my transmission time, difference between my transmission and the internet connection by this SDR. So it's good now to show you that we are transmitting and actually our message is receiving in this SDR. So this was what we have done in our circuit, in our transceiver. I'm gonna now show you the circuits behind, the modifications and the schematics we did to achieve this phone mode in our circuit. So stay on with us few more minutes. Thank you so much. So before starting the explanation for our upgrades, it's important to come back to the previous part to give some explanation about the previous circuit for CW only mode. So we have here the main board. In the main board we have the brain, it's our microcontroller, the STM32F108. We have here the receiver IC, which is our SI4735. We have an audio amplifier for the speaker output and the DDS generator, which is based in the SI5351. Good. We have also the DC regulators here and so. The next one is the power amplifier. So here basically we can generate the carrier for our CW transmission. And this output, this carrier output, goes directly to the power amplifier. In the power amplifier circuit, basically we have a preamplifier and the output amplifier here. And next we have our low pass filters. So in the previous version and in this one, we did 4 different setups. One setup for 80, one for 40, for 20, and for 30 meters. So we have 4 different bands in our operation. We have here a SWR bridge to measure our SWR and a switching relay to switch between transmission and reception. And of course the output, the RF output connector. So basically this was what we have done. We have also the display, the operator interface itself, and the keypad, and that's all for the previous version. Now we're gonna show the updates, the next version. So now in next version, we integrate some more electronics here. So I'm gonna explain the PCB we assembled here. Okay, basically in this board here we use some ICs here, which is our conversions here. Okay, so we have 2 conversions for our SSB generation for our phone circuit. Okay, we have here an audio amplifier, the first one for amplifying our microphone itself. After this audio amplifier, I'm gonna explain by the circuit. We have here the first conversion, which is a a modulator here, a balanced modulator here. Okay, the NE 612. We made the first conversion here to 10 megahertz. So we have to use now two outputs from our DDS, as you can see here, instead of only one from the previous versions. So in the first, as you can see here, in the first clock configuration, I'm gonna show in another picture which can explain you better. So the first output, this output goes to a relay, and this output goes directly to the power amplifier when we want to use the CW mode, and we don't want to use the CW mode, we switch to this board. So the carrier from the channel 0 comes to this board and goes directly to the first balanced modulator here, for the first mixer here. Okay, and in this mixture now we generated our IF, and here we have a ladder filter, basically with 4 crystals. I'm gonna explain some tips here as well, and at the very end we have our second conversion, and from the second conversion the output goes to the same relay, to the other side of the relay, and this basically will send the RF signal to our power amplifier. So this relay basically switches between CW mode, in this case the channel 0 from our DDS goes to this relay and goes directly to the power amplifier, the carrier itself. In the second mode, when you switch to the other side of this relay, the RF generated by the DDS goes to this circuit, to this double conversion circuit. Okay, and the output itself goes to the power amplifier. So it's basically this what is done here. We are not using this filter. This was just for some tests. Okay, and that's it. This is the other side of the board. Okay, some very important hints. Okay, the preamplifier here. So we're gonna operate it now with phone. So in some cases we will made longer modulations than when you are using, for example, the basic CW modulation, which is more faster. And in this case, it's important, it's an advice to use some heatsink. So I made a Homebrew heatsink, as you can see here, but it works fine for that because our preamplifier it's based on the TO92 packaging. So I assembled this to have a proper heatsink for my TO92 preamplifier. So in this case now it's working fine, and I can modulate and I can transmit information for some seconds here without any problem. Okay. The DDS, as you can see here, basically we connect the two RF cables, okay, coaxial cables, 50 ohms directly to the channel 0 and channel 1. So channel 0 goes directly to the power amplifier when we are operating in CW mode, and goes to the balanced modulator, to our newer board, our upgrade, when we want to operate in phone. The channel 1 goes directly to the second balanced modulator, to the second conversion. Okay, and I'm going to explain this next. All right, the circuit itself. So as I explained before, we have here, first of all, a voltage regulator, okay, to generate 6 volts based on the 13.8 volts, our input voltage. This generates the correct voltage for the both ICs, okay, our mixers, our NE 612. Okay, we have basically here amplifier for the microphone. The microphone here, it's not an electret microphone, it's a microphone standard from the PTT we use in citizen band radios. So this is the preamplifier. We have here a potentiometer to adjust our audio level, and this goes directly to the input number A from the balanced modulator from our conversion number 1. The conversion number 1 here, Okay, we mixed our audio input signal to the carrier. The carrier we input the carrier in the pin number 6. So we use this network here, as you can see, attenuation, and also here we use a capacitor, okay? And this goes direct to the relay. The relay itself basically switches between the two functionalities, the CW or the phone mode. So in the first case, when we are not basically setting this relay, okay, you can see that this relay it's connected between the power amplifier and the channel 0 of our DDS directly in this way. So in this case we are operating CW mode, but as you can see here we have the microcontroller and the output configured pin PB5. It was configured in our software as a switching output pin. So in this case we switch between the phone mode and CW mode, and when you operate in phone mode, both switches here changed its position and the output from the DDS now goes direct to the balanced modulator number 1 here. Okay, so we generate basically here a proper carrier for our crystals. It's something close to 10 megahertz. Remember, very important in those SSB filter circuits. You have to purchase those crystals from the same supplier, from the same batch, and test it to make sure they have the same cutting frequency. In my case, those crystals was close to 10 megahertz, was 9.9975, something like that. So I measured them, they are the same batch and very close frequency, cutting frequency. So it's very important, really necessary in our circuits for that. We choose the proper capacitors here for narrower our filter output. So using those values, 100 picofarads here, 100 picofarads to 121, we generated 2.4 kilohertz approximately filter. So it's a very good filter for SSB, for audio, for phone transmission, for phone mode. Okay, so we make a mixture between the audio inputs and the carrier here for the first stage, for the IF. So this is what we have done. This goes to this ladder filter, and next it's coupled by this capacitor to the second conversion. And very important, the second conversion. The output from the second conversion goes to the relay here, because when we operated in phone mode, this relay switches the first input from here to here, the second input from here to here. So in this case, the path of our signal goes from the DDS to the first conversion, generated here the 10 megahertz with the audio. So here we have the modulation, the SSB filter, and in the second conversion, we put in the frequency we want to operate. So basically, as you can see here, the second output from our DDS goes by this network to the input number 6 of this balanced modulator. And we have the mixture of this IF frequency with the audio, okay, our SSB filtered signal. When you mix this to a proper frequency, we generate the output, our baseband signal in 7 megahertz for 40 meters, in 3.5 megahertz, for example, 3.6 megahertz for 80 meters. So our circuit here, it works in our circuit for 80 and 40 meters band, very fine. All right, so we have here a basic explanation of this circuit, and I come back now to the software side. Okay, in the previous videos from the GAMBIARRA one, we explained a little bit what we did to generate this software, and now we made some modifications. We update this software in order to work in the newer proposal as well. So basically what we did, we made some changes here as the phone relay, the newer one, to switch between CW mode and phone mode. Okay, we work in 2 different bands in this case in phone mode, as I explained before. In the 8 meters band, as you can see here, we work in phone mode, and also in the 40 meters band, we work in the phone mode. In the other bands, I was not working in this project, only in 40 and 80 meters band. But of course, based on this project, you can change and you can modify the circuit to operate in different bands as well. Okay. Another things we have changed here, and it's very important to explain this. As you can see, it's very important to understand the concept between the SSB filter. Okay, and as you can see here, just to show this, which is very important, we have to measure anyway using a proper diagnosis tool like oscilloscope and FFT, using spectrum analyzer, okay, itself. But it's very important to analyze this filter. Okay, you can use nano VNA, for example, to analyze this. It's very important to analyze the frequency response of our ladder IF filter, 3 megahertz filter. In my case, this filter was tuned with those capacitors from some frequency bands. So in my case, this filter goes from 9 megahertz dot 996 kilohertz to about 9 megahertz 998 4 kilohertz, 8.4 kilohertz. So this is very important to find. Okay, when you find this, you can generate your frequency in order to generate properly your SSB signal in lower sideband or upper sideband. So for lower sideband, we choose the right most place of our filter curvature, okay, shape. So I use the end of our filter, which is basically this frequency here, and when I use this in the first conversion, I transpose this in the frequency domain, and I capture the lower side of our modulation, of our voice, okay, our information. Okay, in case of USB, it's the opposite. So we choose basically the leftmost of our band shape, okay, from our filter. And in this case, when you have the first mixture, when you have the first convection, our audio is transposed to the frequency side, to this lobe, and we capture the right side, okay, not the left one. So this is the upper side band. Basically, this is the interpretation. And we have to generate for the second mixer. And in the second mixer, quite easy here, you just choose the same frequency you choose from the previous one, from the first conversion, minus the transmission frequency. So if I'm transmitting 7 megahertz, I'm gonna choose 9.9984 minus 7 megahertz. So this will generate the rest we need in the second conversion, okay, to transpose our basically 99984 megahertz signal to minus something close to 3 megahertz to generate the 7 megahertz, because 7 megahertz the our transmitter frequency, 10 megahertz approximately, 10 megahertz minus 7 megahertz, 3 megahertz. When you mixture 10 megahertz with 3 megahertz in our second conversion, we generate two signals here basically. One signal in 13 megahertz and another signal in 7 megahertz. And we're gonna send this. It's important if you wanna choose an output filter for that before the power amplifier. You can use basically, for example, a band pass filter. Okay, so in order to avoid unnecessary frequencies to your power amplifier, I didn't use here, it's a QRP, low power transmission, but instead in the output I have my low pass filter to avoid this result of my second conversion, the other frequency, the frequency I don't want to transmit here. So this is basically what we have changed, something more here in the software side, but I don't go in the details right now. So I hope you enjoy this. You can have this project in your hands. I basically I'm gonna upload this in my website, in the tutorials area of my website, and you can for sure download that and assemble your own transmitter. So thank you very much again for watching this video. See you next time.